From the smartphone in your pocket to the radio waves that carry your favorite songs to the medical imaging that peers inside the human body, a single, elegant set of 5 equations underpins it all. These are Maxwell's equations, the bedrock of classical electromagnetism and a cornerstone of modern physics. Ready to decode the universe? Here are the 5 physics Maxwell's equations you must know. Number 1. Gauss's law for electricity. This is the starting point, the fundamental rule of electric charge. It states that electric charges are the sources of electric fields. Imagine a positive charge, like a proton. It radiates electric field lines outward in all directions, like a tiny sun. Now, picture a negative charge, like an electron. It pulls those field lines inward, like a cosmic sink. This is the very reason why opposite charges attract and like charges repel. It's the force behind static cling that makes a balloon stick to the wall after you rub it on your hair, and it's the principle that governs how capacitors in your electronics store energy. It's the universe's way of saying charges create fields. Number 2, Gauss's law for magnetism. Here's where things get interesting and a little mysterious. This law tells us something profound about magnets. There are no magnetic monopoles. While you can have an isolated positive or negative electric charge, you can never have just a north pole or just a south pole on its own. If you take a bar magnet and cut it in half, you don't get a separate north and a separate south. You get 2 smaller magnets, each with its own north and south pole. This means that magnetic field lines don't start or end anywhere. Instead, they always form continuous, closed loops flowing from the North Pole to the South Pole and back through the magnet itself. This simple but powerful rule explains why compass needles align with the Earth's magnetic field and is fundamental to the design of every magnet, from the ones on your fridge to the powerful superconducting magnets in particle accelerators. Number 3, Faraday's law of induction. This is where the magic of motion comes into play. Faraday's law reveals a deep connection between magnetism and electricity. A changing magnetic field creates an electric field. Picture a coil of wire and a magnet. If you move the magnet through the coil, or even just change the strength of the magnet over time, a voltage is induced and an electric current begins to flow in the wire. This is the principle of electromagnetic induction, and it is the engine of our modern world. It's how electric generators at power plants work, converting mechanical motion into electrical energy. It's the secret behind transformers that step voltage up or down for power transmission. And it's how your wireless charger juices up your phone without any physical connection, by creating a changing magnetic field that induces a current in a coil inside your device. Number 4, the Ampere-Maxwell law. This is the other side of the coin and the equation where James Clerk Maxwell made his most revolutionary contribution. Originally, Ampere's law stated that electric currents create magnetic fields. This is why a wire carrying electricity will deflect a nearby compass needle. But Maxwell noticed a critical piece was missing. He theorized that a changing electric field must also create a magnetic field, just as a changing magnetic field creates an electric field. This addition was the key that unlocked everything. It meant that electricity and magnetism were not separate forces, but 2 aspects of a single phenomenon. One could create the other in a self-perpetuating dance. This single idea completed the set of equations and predicted the existence of something extraordinary. Number 5, the wave equation. This isn't a separate law, but the grand finale, the ultimate consequence of putting the other 4 equations together. By combining Faraday's law and the Ampere-Maxwell law, Maxwell derived a set of wave equations. He calculated the speed of these waves and found it to be a constant, determined only by fundamental properties of space itself. The value he calculated was approximately 300,000 kilometers per second, the speed of light. This was no coincidence. Maxwell had unified electricity, magnetism, and light, showing that light is an electromagnetic wave, a ripple of oscillating electric and magnetic fields traveling through space. This discovery not only explained the nature of light, but also predicted a whole spectrum of other electromagnetic waves, from radio waves and microwaves to X-rays and gamma rays, all traveling at the same cosmic speed limit. The applications of these equations have profoundly shaped our civilization, especially in the realm of biomedical instrumentation. Take magnetic resonance imaging, or MRI, a cornerstone of modern diagnostics. MRI machines use powerful magnets to align the protons in the water molecules of your body, a direct application of Gauss's law for magnetism. Then, they use radio waves, a form of electromagnetic radiation predicted by Maxwell's wave equation, to knock these protons out of alignment. As the protons relax back into place, they emit their own radio signals, which are detected by antennas. By precisely manipulating and listening to these signals, a computer can construct incredibly detailed images of soft tissues like the brain, muscles, and organs without using any harmful ionizing radiation. It's a symphony of Maxwell's laws playing out to save lives. Another critical application is the electrocardiogram, or ECG, which measures the electrical activity of the heart. The muscle cells in the heart polarize and depolarize, creating tiny electric fields that propagate through the body. This is a direct manifestation of Gauss's law for electricity. Electrodes placed on the skin can detect these minute voltage changes, which are then amplified and displayed as the familiar sawtooth pattern of a heartbeat. Doctors use this to diagnose arrhythmias, heart attacks, and other cardiac conditions. Similarly, electroencephalography (EEG) uses the same principles to measure the brain's electrical activity, helping to diagnose epilepsy and study brain function. Even technologies like electrosurgery, used to cut tissue and cauterize blood vessels during operations, rely on Maxwell's principles. These devices use high-frequency alternating currents to heat tissue very precisely. The flow of current, Ampere's law, and the resulting electric fields, Gauss's law, are carefully controlled to achieve the desired surgical effect with minimal damage to surrounding areas. From the fundamental waves that carry our information to the intricate devices that monitor our health and treat our diseases, Maxwell's 5 equations are the invisible script that governs the technological world, a testament to the power of a few lines of mathematics to explain the universe.